Okay, so the next thing which you want to do today is two more plots, right? Two more plots. So we saw heat maps. We saw. So Whitney, can you see my screen?
Yes, sir, I see your desktop.
Okay, yeah, desktop. So so last time we tried to look into some techniques of generating heat map. So today's right. So we did use this data, GEO country dataset CSV file, and then we just try to play around with data, removing the missing values, selecting or subselecting columns, then making a correlation plot, and then making heat maps using two libraries. First library we used was R color brewer, and the second library we used is P heat map. And just a note, to make a heat map, we at least need 3 columns. One would be the names, and 2 columns would be your numeric columns. And make sure you don't have any NAs or missing values in your data. That will give an error. So that's a heat map. So I think there are more things which you can do with the function, right? So you can change the color palette, or you can change the labels. You can assign the legend. You can change the legend colors, label colors, right? So there are n number of things which can be done by these two libraries, pheatmap and R color brewer. But I think so. I just wanted to give you like a basic idea of how to make a very standard basic heat map. So do we have any questions on heat map? No, right? So I will possibly give you an data. So I will, and this is how I will give you, right? So I'll have more than 3 columns in this file. So I'll have like say 10 columns, just to make it tricky. So I'll have like 10 columns in this file. I will ask you to generate a heat map using any of these libraries on selected 3 columns, right? So from 10 columns, you have to do some selection with this statement. Then there would be some missing values in the data. So you have to do any omit. If they are not numeric, which we didn't have here, right? So that issue was not present here. If they're not numeric, then you have to convert it into as.numeric, and then it will convert your floating or double values into numeric values, and then you just follow these statements to generate your heat maps. Once you have your heat maps, you submit them as your answers, right? And that's a heat map. So the next 2 things which I want to discuss is this plot here, right? So these are called as pie chart, right? Pie plots, pie chart. These are also very useful plots because you can. It's easy to summarize your data by filling in the circle, right? So these can be like actual numbers, right? So this is the density. It's the density of points, right? So this can be density, the raw values, or it can be percentage, right? Or it can be like some absolute numbers, right? So you can fill in these sections, and it's a very useful, informative plot, which I want you to to generate, right? So that's our next plot, and the last plot is the volcano plot. This is the volcano plot. So have you seen this plot before? No. It looks like a volcano, right? So it's called a volcano plot. It's a very standard plotting for for the biology, right? So biology, we have the gene expression experiments like sequencing or microarrays. So in them, if you have like a fold change for the genes, and if you have the p-value for the genes, then you can take these two columns and generate a volcano plot. Uh, it's it's used to understand the outliers, right? So which, say for example, there would be like some points here or these points, right? These can be, so they do not fall on the on the on the curve, right? Distribution plot. So this may be a normal distribution. They may not be falling on this normal distribution curve. So they can be outliers or they can be some interesting genes, right? So if you have two columns, right, not just the biology gene expression experiment, but any two columns, like a fold change or a p-value, or like adjusted p-value or a z-score or a t-score, right? You can take those two columns and generate this volcano plot. So I want you to show you how to make these pie charts. It's very simple to make a pie chart. Just 3-4 sentences, statements in R. It will generate a pie chart, a very basic pie chart. And then I wanted to show you how to generate a volcano plot. So to generate a pie chart, what we will do is we will just use the same sample data. So what we will do is open a new R script and make the R script as today's date, which is March 2. March 2, desktop. The first line is your comment. See the author, date, author, date, and the purpose. The purpose is generate pie charts and a volcano plot. Okay. So that's your first line. Save your R script, and once you're done with the class, you can upload this R script. So to make this plot, we just need some classes, right? So let's make some. So let me just copy some of the statements from this tutorial. Okay, so the first thing is to create a list of elements, slices, as follows. Next is to create a list of labels, create a list of elements, or say labels, called labels, as follows. And the last is the function, labels, as follows. And following is function to generate a chart. Control S. Okay. Okay, that's it. That's the code for generating a pie chart. So the first thing which you want to do is you want to create the list, the elements, right? So in the pie chart, you would have those, you have the sections, right? So you have like a section for each label. So 10 is the section for a country US. 12 is the amount of section or the region for country UK. 4 is for Australia, 16 is for Germany, and 8 is for France, right? So you're just assigning how much region on that pie chart you want to allocate for each of these labels, right? Assign for each of these labels. So these are just raw numbers. So you can assign raw numbers. You can also assign percentages. You can assign fractions, right? So there are different ways of assigning. It depends upon the user preference. But then in this case, we are just assigning the raw numbers. And the labels we want to plot are US, UK, Australia, Germany, France. So you would have a pie chart with US with like 10% of the area, UK with 12%, Australia with 4%, 16% is for Germany, and 8% is for France. So we have slices and we have labels. And then you use the function called pi. So pi is a function which is just coming from R. We are not using any external library here. So there are some libraries like ggplot2 also does pie chart, but this is the simplest. I just want you to know that there are these pie charts which you can do in R. So you use a function called pi, and then it asks for just two arguments. First is the percentages or numbers, and the second is your labels, right? So labels is your labels with your respective numbers, and the main is just the title for your pie chart. So that's an optional argument. So pi takes in two arguments. First is the slices or the numbers, and the second is the labels for the slices. Okay, so let's run this. Run these three statements, and we should have a pie chart. Something like this, right? So, good, you have a pie chart. So then, you can. There are some limitations here. Like, so in this case, you just have like 1, 2, 3, 4, 5 labels. I think like you can have max maybe like 50 to 100 labels. I don't know. But then if you add more labels, then it's not informative. It gets overlapping, right? So it's just like heat map x-axis. So there are some limitations of these plots. I'll try to like limit the labels to say 50 labels or less than 100 labels max. And then these are the regions, right? The density, it corresponds to the values. And you can also like assign your custom colors. So pi, it has like an argument here somewhere. You can adjust colors, you can adjust the angle, you can adjust the if you want to have like a clockwise pi or an anti-clockwise pi, you can adjust the radius, you can adjust the edges, the size of edges, right? So let me show you like what does angle do. Angle, say if you add like say 120, let's see what this does. Pi of 120 did not change anything. Pi of 90, do you see any change? No, right? So what does angle does? Angle of 45. I don't know. It does something. I'm not sure what it does. Angle. Angle adjusts the slope of shading lines given as an angle in integers. Angle adjusts the slope of shading lines, okay, given as an angle in degrees, counterclockwise. Shading lines, okay. Mm. Clockwise, C-L-O-C-K, clockwise, if true slash clockwise. Clockwise. Okay. Okay, do you see a difference in these two plots? What's the difference? Hmm? Yeah, it's the mirror, right? So if you start with the US, France, Germany, US, France, Germany. So one goes clockwise and the other goes anti-clockwise. So that's your, that's the clockwise argument. And I still don't know what is angle. Can you figure out what is the angle thing doing? So let's do like angle of 90. It does not seem to make any change there. Yeah, I think it's probably so the angle is used when there are like shading lines. So we don't have shading lines here. So probably it's the angle of shading lines. So if you have shading lines in there, then it will change the angle of those lines. That's the description. But we don't have shading lines, I guess. So if you have this chart, right, I just want you to know how to make a pie chart using this function called pie. And you pass in the first argument, which is your numbers. Second argument is your labels. That's all. And then you should have a pie chart. And save your pie chart. And then once done, you can upload it on your repository. Okay, so this is done. The next thing which I want to show you is how to make a volcano plot. Volcano plot. And to note, volcano plot, it is usually used in gene expression analysis to find significant genes, significant or say important genes, in your samples, right? Samples, and it is usually plotted on two columns. First column is a p-value, and the second column is the log fold change. That's all. Okay, just to make a note, what is a volcano plot? And it is usually used in gene expression analysis and to look at the interesting genes, and it takes in just two columns, p-value and a fold change in terms of expression analysis. Okay, so let's generate a volcano plot. To do that, we have some sample data which I want to use from this tutorial. So I'll just make some sample data set here. Temp. Yes, please. And should do your volcano plot using plot. Okay. So the first thing which I'm doing is getting a sample data from Git as follows. Next thing is okay, before you do this, set your working directory. Set working directory probably to whatever desktop, my desktop. Set WD. Next, read the downloaded data in R. Next is convert to complete cases as follows. And the last is following to generate a volcano plot. Okay, that's all we need to do. So first thing I need to do is set my working directory. So terminal cd desktop wd, set my working directory. Somewhere on desktop. Okay. So the first thing which you want to do is line number 15. Set your working directory to like desktop or documents or downloads, right? So I hope you know how to do that, right? Set your working directory to say desktop. So my desktop is on this path, users desktop. And the next thing is you want some dummy data. So type in the statement here, statement number 18. It will just go into this link called raw git. So there's one GitHub link where you have data for plotting a volcano plot, gene expression data. Then you download this, then you read the downloaded data using a read RDS function. Then you do something called as complete cases. I'll explain what is complete cases. And finally, we use our library ggplot to make this volcano plot, right? So just type in these things and let me know when you're done. And then I'll just explain you. Save your R script.
Does it go any more over on the side? To get sample data?
Sample data.
Like, does the whole line just start?
This is just one line. After this forward slash, you have this master, one line. Okay, so type in and run it on your console. Make sure you set your working directory to your desktop or your downloads or your documents, any folder, right? And then you should have a plot.
Mine is giving me an error. Oh,
Okay, you have a plot?
mine is giving me an error.
What's the error?
GG
Not found.
plot function.
Okay, mine also gives me the error. The ggplot too. Oh yeah. Yeah, I forgot to import the library ggplot2. Try this. Yeah. So just import the library. We did install last time, so we should have it. And then run it. Yeah. Okay, so let me just make this plot. And if you have this plot, save it as Volcano Plot. Yeah, save it as Volcano Plot. Okay, so now I'll just explain you what I've done here. So the first thing I wanted you to do is set the working directory. The reason is the next statement here is download file. So this statement is going to go to a link to a page, and it is going to download some data. So we want to know where this data be downloaded in, right? So that I don't know what is the default directory when you open R, but every time you want to get any data, download any data, you just you make sure you know where the location is, right? So I want to download this data in, say, my directory called desktop, right? So make sure you know the location of your download. So that's the reason I asked you to set your working directory to desktop. The next statement here is the function called download.file. Now this is a new function. I'm not sure if we have discussed this function before. So download file is a function which will take in the first argument as your web link, right? So you have a web page, you have like an FTP link, you have this HTTP page, right? So it will try to go to this page and look for any of the files. So in this case, what type of file do you think is this? So you see this file DDF for volcano.rds. Is it an Excel file? Is it a text file? Is it what format is it? Any guess? Word? No. RDS. .rds. Very specific to R. Yeah, R data format file, right? Our data set file. So R data, it's very specific to R, and it can only be read in R. It's an R data file. So someone has exported their data in this R data format file. So it's easy now, since you're working with R, the only R users can import this file. So that is what we are doing, right? It cannot be imported in Excel or Word or text editor. It can only be imported in R. So it's an RDS specific format file, which is what we want. So that's your first argument. First argument is just pointing. It's a pointer pointing to a web page which has this file uploaded from some Git user called df for volcano.rds file. The next argument, next argument here is the name of this file which we want to store in, right? So we want to download this file. So we have an option to save this file with same name or with different name. And we can even try to save it with like a different format. So in this case, you can save this file in CSV format. You can save this file in text format, right? So you have an option of downloading this file in different formats, but I just use the same file name and same format. And the last argument is curl. So curl is a method of downloading your data. So there are different methods or techniques of getting data. One is curl, one is wget, right? So there are different ways you can get the data. So so just make sure you have this argument called method. It is one way of downloading your data. Cool, right? That's your function for downloading a file from a web link. So now once you run this statement here, number 18, you should have a file called ddf-volcano.rds on your desktop. Right, so I see this file here now, and you should also have this file on your desktop. Now you see that this file, the symbol for this file is R with like some container, right? So that's a very specific RDS format. So whenever you see this RDS format, it's like it's a very R specific file, right? So it's a data file. So it's giving like a container with R symbol there. So that's your R data format file. Right, so anytime you see this weird symbol file, you just you should like you should know that this is you won't be able to open it with any other editor except R, right? So this is just one way of storing your data. The next thing is read RDS. So this is also a new function. Read RDS. So we have read.csv. We have read.txt. Similarly, for a RDS format file, we have a function called read RDS. That's all. And the argument it takes in is your file name, which is ddf for volcano.rds. And I'm just storing it into a variable called tmp. You can have any name for this variable. The next thing is complete cases. Okay, so this is also new. So what is complete cases? what is complete cases in R. So there's a function called complete cases. So just to give you an example, okay. So in this data here, right? So in this data, you see that it's similar to our heat map data. So if you remember that we had a country column, we had a latitude column, and we had that weird, yeah, that column, right? So three columns. So the first line had missing values. So you had these NA values in that data, NA values, which is similar to this data here. So you have NA, which is like empty cell, no value, NA value, empty, NA value, empty. So you can do NA omit, or you can do complete cases, right? So NA omit will remove the entire line number 5, will remove the entire line number 6, remove the line number 10. The same thing can be done with complete cases, right? So complete cases removed this line number 5. Complete cases removed should remove line number 6, should remove line number 11, right? So I'm not sure how this, we got this. Complete cases 1, right? Okay. So complete cases in this case, this user is only assigning to column 1. So wherever you see NA value in column 1, that row would be removed. So the only difference between NA omit and complete cases is, with complete cases, you have a flexibility of omitting certain columns. That's the only difference. If you use NA omit, any row which has a NA value would be removed, right? Just to make it very easy, whiteboard. What's the difference between two functions, NA omit and NA omit and complete cases? Complete cases. Okay, so if you have like a data here, data frame with just say 2 columns, 2, 4, NA, 6, 1, 2, 4, NA, right? So if I apply NA omit here, what would be the output? So what you will have a first row? 2, 1, and next 4, 2, and 6, 4. Will it have?
It's going to get rid of the rows with many values.
Yeah, so it will get rid of this and this, right? That's your NA omit. So wherever you see NA, remove no row. Wherever you see NA, remove row. And then you only are left with 2, 1, and 4, 2. With complete cases, you have a flexibility. So if I apply complete cases on row 1, what do you think would be an output? complete cases on row, sorry, complete cases on column 1. I'm sorry. Complete cases on column 1. So I'll have 2, 4, 2, 4, 6, and anything in second column? 1, 2, NA. Right? So I'm just applying complete cases on column 1. So wherever you see NA in column 1, it will remove that row here. And you're just left with 2, 4, 6 NA, right? It's not touching second column. That's the only difference. So you see, there are these functions which help us to be very flexible working with your data frames. So I'll just make a snapshot here, and probably this would be a very interesting question for your exam. Okay, that is done. Leave. This is done. There. All right, so that is what we are doing here. We are just applying complete cases, and then we store it in a variable called DE, and then finally we just pass in the DE into a function ggplot, and the AES are just the argument which takes in the columns, right? So X column is log to fold change, Y column is p-value. So just to show you what we have here is, I'll just do head of DE. So in head of DE, you see that we have 3 columns. The first column is gene symbol. Now this data is very similar to our previous heat map data, country data. So instead of country, we have gene symbol, we have log to fold change, and we have a p-value. So we are going to do a plot, volcano plot on p-value and log fold change. That's it. So this is the data which we downloaded. Dimensions are, so it has around like 13,421 rows, and we have 3 columns. First column is gene symbol, second column is log fold change, and third column is p-value. So in ggplot, we pass in data as DE, and then we on 2 columns, log fold change as your X column and p-value as your Y column, and GE, this is just a point where you can make changes to the font of your point or the size of your point. So it's an optional argument. And once you run this, then you'll end up with this plot. Now the X and Y scale are, these are like, you can change it, right? So you can have log fold change as your Y scale and p-value as your X scale. So in this volcano plot, you can change the axis, but you should end up with similar plot here. And that's your plot. So there are different things again. For example, you can, if you're interested in, say, these points here, like 1, 2, 3, 4, 5, 6, 7, you can label these points, right? So what is this point? What is this gene name? What is this row 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 name, right? So you can label these points on the plot. And that is what you will see in some of these papers, right? In these gene expression analysis papers, they show these plots, and they also try to label these points, right? So these are like some interesting points, interesting genes. So what is this point? So they will just label this this point. I don't want you to do that. It's not needed, but that can be done here, right? So you can make this plot more informative. You can also add colors. You can add like some like a legend here, right? So you can have like say the highly expressed genes can have like red color the low expressed genes can have like green color, and then the insignificant can be black color. So you can add that color label or color legend on this plot. So it's many things can be done. Just to give you an example, I'll just show you one paper, right? What is its use? Many people use this, and probably if you work with similar data, you can also try to make these plots in your thesis or in your paper. Say, let's do microarray volcano plot, something like this. Comparative transcriptome analysis. Right, so this is one paper. It says like comparative transcriptome analyses identified the molecular signatures on regulatory networks and chloroclast and osteoclast. And these are the figures for this paper. And if I just open this figure number 3 here, you see this whole volcano plot, right? So this is similar to what we have done. They just have scaled it, right? So this is their 0 scale for log fold change. Yeah, this is log fold change on X scale. And then the Y scale is your p-value, right? So p-value is your Y scale, log fold change is your X scale, and they have like made like a center for their X scale. But this is a volcano plot which you can generate in R. And they also have a heat map. So now you know how to make a heat map, you know how to make a volcano plot, and you also, I guess, know how to make these bar plots in R. Right? Any questions? You good? Right. So what I want you to do is just save your 2 plots, save your pie chart, save your volcano plot, and save your R script, and also save the data. So you should have downloaded this RDS data, right? So you should have your R script, pie chart, volcano plot, and the data. And you just upload that to your Git repository.
You want us to upload the data too?
Yes. Yeah, you think you can upload it on your Git. And then, yeah, that's all I need. And then we are done. And I will also do the same. Or quit, don't save, GitHub. Stat 302. Add a file, upload files, RDS data, then the screenshot, then the pie chart, volcano plot, and the script. Commit. Processing. Okay, that's all. If you don't have any questions, we are done, and we will start a new topic on Monday. Any questions, Whitney? Okay.
No, sir, I got the plots uploaded.
Okay, thank you. I'll see you on Monday.
All right, see you then.
March, volcano, pie chart, screenshot here. Move trash.
Have a good one.
You too. Stop share. And exit. Sign out. And